Hello again, everyone. So our next session is from an organization called MasterShip, and they're going to be talking today about automating class-compliant ship construction design using AI. So great topic, over to both of you.
Yeah, thank you very much. Indeed, welcome everybody. We're going to talk about the topic of today, automating class-compliant ship construction design using artificial intelligence, a new paradigm for ship design. So my name is Gijs van Beek. I work as a project manager at MasterShip for about 5 years now. With me is our director, Jacques. Um, he works at MasterShip for since 1986 because he's the founder of MasterShip. So this year we have our 40-year anniversary. And at MasterShip, we have two sides of the company. At one side, we do software development to make software to make ship constructions. And on the other hand, we do engineering, and we use our own software that we also sell in order to do engineering jobs. So the topic of today, automating class compliant ship design. Let's dive in by looking at the design process first. Looking at the design process of a ship, we see that that is very much rule driven. Rules are coming from really everywhere. So it can be the general arrangement and the design specifications, class rules, yard rules, work methods, any other rules that you can imagine, really. So we see those at the top of the image. And those are input for, they really drive the ship design itself. That leads to two effects, namely on the left-hand side, it leads to frequent rule compliance checks because every design specification, each ship is unique. So we have to time and time again check for all the rules and to see if we are compliant. This leads in turn to a slow design process, which is not a desirable outcome. On the other hand, those rule sets are so big that we simply cannot overlook them by a human. And that results in an experience-driven approach. Like we did what we always did, just in order to make it easier for ourselves, which is normal because we are humans. And this experience-driven approach leads, unfortunately, to little innovation and optimizations in ship design. Also, an undesirable result, which leads me to the following problem statement. We want unique class-compliant ships, but also innovation and an efficient design process at the same time. Now, with the coming of large language models, artificial intelligence in general, we are able to interpret the rules that are written for humans, so text, into machine readable code. So computers can now interpret rules and documents that are written for humans. And that gives us two potential solutions to this problem statement. The first is that because the whole shipbuilding process is so much rule driven, it also becomes predictable. And once it's predictable, we can automate the process of construction design within all those class rules and other rule sources for the design specification. And that leads to class compliant ships and first time right designs. So that refers to the efficient design process. And on the other hand, I already talked about it, is to optimize within the specified design rules. There are so many rules that a human cannot oversee them. It's just too much. So we cannot optimize. It's too much for a human. But now that a computer can understand all the rules, we can oversee it because this computer is able to oversee all the rules. And because we can oversee all the rules, we can also optimize within those boundaries, and we do not have to do what we always did. We can experiment without doing checks over checks over checks. So today we are going to look at the approach that we took in this challenge and where we are standing today. And I want to show you some developments that we already actually did. First, we are going to take a look at the ambitions that we have in this perspective. What we are striving for is a rule-compliant 3D model and building kit, automatically generated, starting from only the general arrangement and design specification. So this is our broader vision, and it might be a bit of a high aim. Nevertheless, this is the direction that we believe we should go in, not to achieve the goal itself, but to make practical implementations along the way for our software users. So it might be not about the goal, but about the practical sub goals that we have in it.
Guys, I like to give a short remark here, huh? Because now I see the building kit is dropping in, yeah, and maybe it's good to mention here that the core business of MasterShip is in fact the work preparation and creation of building kits, yeah.
Yeah, that's indeed.
And of course we can never be on that island by ourselves. We have to look around it, huh? And we do this building kit business by projects and by the MasterShip software. Yeah? But preparing this, then we are strongly depending also on the rules and that kind of things. But just to make a little bit clear where the building kit is coming from. That's in fact our core business. Yeah.
That's a good remark. Yeah, thanks. So I'm going to show you what I'm talking about in a nutshell. We made this graphical diagram. So our ambition consists of 3 stages. In the first stage, we are gathering input, so the documents, generation plan, design specifications, class rules, all kinds of different rule sources, and they are usually just in PDF format. Then the second stage is to give all those documents as input to our artificial intelligence tool. This artificial intelligence tool extracts and determines the right design parameters based on the given input documents. And using those design parameters, we can establish the 3D model in the third stage. So today we are mainly going to look at the second stage, so the artificial intelligence tool for the determination of the design parameters based on the PDFs. Before we are going to dive into this tool, I want to show you why you think this is a feasible goal to achieve. First of all, I said it earlier, we have those technology advancements in natural language processing, which is sort of the core of large language models, and artificial intelligence. And this really helps us to make the interpretation of all those rule documents. Then we already have this program, Tom, which helps us to generate a 3D model from the design parameters. And finally, there's a third item in place, that is the semi-automatic conversion to build kits already exists. So with the first item helps us for the parameter determination. Let's take a look at how that exactly works in more detail. So here I have this image displayed as a linear process from the left to the right. In reality, it might be more circular, but we displayed it as a linear process. So on the left, we are starting with those input documents, which are again usually just PDFs. And they are interpreted by the artificial intelligence tool and stored into a rule set database. And this is actually the same technology that large language models use. Then from this extracted rule set database, we automatically extract formulas and rules that apply to the design specification. And that is something new. That is not something that large language models do. So once we have those formulas and rules, but also coefficients and anything that is applicable for making the design. We can now also optimize within those boundaries. So those formulas and rules, they form sort of the boundaries of our solution, and we can optimize within those solution for our ideal design parameters. So we could either optimize for weight or cost. And that finally leads to an optimized design solution. And with those parameters, we can make a 3D model. So where do we stand now? We stand here at the first, or it is highlighted 3 steps. We have made practical implementations for those 3 steps. So the interpretation, the extracting of formulas, and finally to get a design solution. The other 2 parts we skipped because we see that the conflict of rules is usually small. Like it could be that there is a conflict between Lloyd's classification rules and some rules that are typically used at the shipyard or something. Those are minor, so we have skipped them. And finally, the optimization of design parameters. We haven't done that automatically yet. But that's also not per se artificial intelligence, because you could also do it with traditional software methods like looping functions. Okay, so great. Me, myself, I'm a big fan of showing and not telling what we have done. So I've prepared a short video for you in which we are going to demonstrate how it actually works. This is the application that we have made so far. And it starts by selecting the right design specification and classification rules. And then we can make some settings like where is the bow of the ship and where is the midship. Once that's done, these documents are being interpreted by the artificial intelligence tool. And at the same time, it finds the applicable rules, formulas, and coefficients to the ship design specifications. And what's unique about it is that it are not only formulas, but it can also be coefficients that come from figures, for example. So the outcome are 3 results. Extracted values directly from the design specification. We see them in white. We have estimated values that we see here in yellow. And we have calculated values for the classification society, which are highlighted in blue. So a user can review those results and make some changes according to what he or she thinks. And finally, what is most important is that we get the output of the construction design parameters and also the weight estimation. And it helps us to save a lot of time, actually. So before this application, you needed to do a lot of searching in the rule documents, which could take you days or weeks in order to find the right solution. Now, this will take you about 15 minutes for processing all the documents and finding the applicable rules and formulas. Next to that, it's also special that all the formulas are not hard-coded into this software, but they are extracted from the input that you give. So depending on the input that you give to this program, you will get a different outcome. And that's really special. And now that we have those design parameters, we can use those to create a 3D model automatically. First, a quick recap of where we are standing. So this is again those 3 stages. We have now looked at those first 2 stages, the input of documents into this artificial intelligence tool, which finally gives us the design parameters. And those design parameters are input for the next step in making a 3D model. So we are now going to look at how convert those design parameters into that model. And we can do that using our software TOM, template-oriented modeling. And this part of software uses parametric design. And That's a bingo because we just extracted parameters. It's fully parametric and therefore we can use it. So this connection from the artificial intelligence tool to the 3D model is still in development, but still I would like to show you why this would be a very feasible method to do so. So I again have prepared a small video on how this program works and how it connects to the design parameters. So here we see this 3D model of the bow area of a ship, in which the position of frames and decks, they are actually taken directly from the design parameters that we just saw in the artificial intelligence tool. So that's a one-to-one translation. In this 3D model, there were a few frames missing, and in this video, we are going to complete those frames. We can make parts using the hull shape and the deck positions, which are again taken from design parameters. Also, the material is taken from the design specifications, and the thickness is a design parameter. That's all the input that we need to create our first part. Then for the stiffeners, it works similar. It uses the main construction elements. The type of profile is again defined by the design parameters that we have seen in the artificial intelligence tool. And also the size of the profile. Here we have some other templates, but it's not too relevant for now. So then finally we can construct this stiffener. And now we already have a frame. And to complete this frame, we can also make brackets, which are more details, but still we like to show how it works. So here we see a template of a bracket with parameters. Again, they can come from this artificial intelligence tool, but in this case, maybe also from yard rules. So maybe this specific shipyard uses a very specific type of bracket. We could also put that in as input to the tool. And there we have it, our first bracket. And then finally, we make a second bracket with a different type of rule set. And that's how we complete a frame using only design parameters and rules. Of course, there was some manual clicking and all, but since those are tagged line entities, we are confident that we can fully automate this process. Then to make it a 3D model, we simply have to repeat the same process for all the other frames in the ship. We could do it manually, but we also have this tool that does it automatically for you. And now we are done. So now we have established 4 frames, or now 5 frames actually, using only the design parameters and rules. So I'm looking at the time and we'll stop this video here. The final step was to update those stiffeners and all, and it again updates, which can also typically happen in early design stages. Now with this, we have demonstrated the final step in our ambition of making a 3D model, and eventually we could also make a building kit out of it. So the first steps are taken. We are still fully developing this tool, but we are also at the same time very close to make our first release to our users. Just need to look at what our next steps would be. Next steps would be to implement for more classification rules. We would like to see also automatic gathering of data like hydrostatics. The interaction with other disciplines is always a big item like piping interior. And again, we would like to make practical intermediate releases for our MasterShip software users along the way. So we'll keep doing that. These were our thoughts about where we are heading in the nearby future. And I'm very curious to hear what your thoughts are. So I thank you very much for your attention. Here on the screen, you see the QR code. If you would like to get in contact with us, you can scan it using your mobile phone. You can either contact Jacques or me. And then there's room for some questions that you guys have that can either be answered by me or by Jacques. So thank you much for your attention.
Brilliant, great presentation. Topic close to my heart around the kind of improvement of around the design tools, and I haven't quite seen something quite like this before in this area. So great to see the work that you've done, and clearly it's got people in the audience interested on many things as well. So there's already been quite a few questions on the loop. So I know, Jacques, you've been answering some of the questions as we've been going through.
I can't keep track with them, I'm sorry, but
No,
I
no,
will
it's fine.
answer them also after our time is gone. Yeah.
No, it's good. It's good. You've been on it to make sure that they're properly answered. So we'll go through some of them as we've got time. So Patrick has been asking, once the design is done, how do humans or AI check or ensure that the compliance with the rules? I think there's another question around this. So how do you make sure that you're doing the check afterwards as well to that it's picking the right elements out?
It's a very interesting question. Would you like to answer, Jacques, or
Yeah,
shall
I like it. I like the question a lot. This is an ongoing challenge by software developers, because if the software is doing the correct job, you must trust it, and it will be complying with the rules. Yeah, and that is a little bit a kind of closed question, and you have to believe it. Huh? For instance, when I compare that with making a hull expansion, when we made the first, let's say, 20 hull expansions, we all checked them if they were indeed fitting the hull. Yeah. But when this software will work and will interpret the rules, it will come with the right answer. And at the moment, to be honest, we also don't trust it. So yes, there is still a human interaction. As Gijs showed our outcome with the 3 colors in the numbers we find, the calculated color, the rule-driven color, and just the color we can override. But that is still how we want to get customized to the software, and we must learn to trust it in the future. At the moment, same when we started to make the first hull expansions, we want to check and there is human interaction. Some other questions were also about the human interaction. Mm-hmm. But I'm convinced that in when you use this program for a couple of projects, you start to trust it, and it will give the right answer because it's software. It's not a human action. Software, when it is doing, of course you must test, and double check in the beginning. But after a couple of years, there will be no doubt about the outcome. Yeah.
Okay. There's questions here around when the rules get updated, whether the tool needs to be retrained again every year. Are you able to just expand on that one again, just because I think that's quite an important question?
Yeah, I can. So this artificial intelligence tool is pre-configured, and it sort of asks the right questions. So if there come updates of the Lloyd rules, then the program will automatically adapt to it. Of course, as Jacques also mentioned, at this stage, we still have to check it if it's correct. That's our job as software developers. But in the end, the software is configured that it can adapt to changes in rules.
Brilliant. Okay. Well, thank you very much again for a great presentation, and thank you for being so hot on it with all the questions answering. If anyone still has any further questions, then they know where our presenters are. So thank you again for a great presentation, and I hope to speak to you as the session goes on. Thank you.
Thank you very much for hosting.
Great talk, both.